Okay, so today we're going to see some substitutions that involve a lot of fractions. Okay, we're going to have to recall our natural log rule. Okay, remember if we have 1 over x, the antiderivative is the natural log plus c. Okay, so see how this is like a house and this is a log. Okay, go ahead and write down this example. When we have a fraction and your denominator is 1 degree higher than the numerator, it could be a nice candidate for U substitution. It may not, but it could be. Okay. Remember Friday I was talking about how we needed a composition times another function. This would still follow that mold because we have x squared plus 1 inside of like a reciprocal function, 1 over something, and then times x. So this still fits the composition times a function, even though it doesn't look like a product. Okay. So, in this case, what would we have to let u equal? X squared plus 1. And if u equals x squared plus 1, then du is 2x dx. Okay, so we have an x dx, but we don't have that 2. So we can go ahead and divide that 2 over. Okay. Some of you are going to get to the point where you do not need to show this particular step right here, and that is fine. Some of you need to show it, and that is fine too. But I always need to see these 2 steps when you do U substitution. Okay, you can't do that in your head. I would like to see that for me. Okay, so then what we can do is we can replace x dx with 1/2 du, and then we can replace x squared plus 1 with u. So now we have 1/2 the integral of 1 over u du. The antiderivative of 1 over u. What's this? Natural log of the absolute value of u plus c. So, what was our original x squared plus 1? So our final answer is 1/2 natural log of x squared plus 1 plus c. Okay. If we take the derivative of that function, we would get back to what was originally inside our antiderivative. So we can kind of check our answer, if you will. Okay. Now, what's true about x squared plus 1? Its value is always what? Positive. Can it ever be 0? No. Okay, so we put these absolute values on here because we need our values to be positive. All right, since x squared plus 1 is always positive, this could be a time where the absolute values wouldn't be necessary. So let's say you're doing a multiple choice problem and you don't see those absolute values. Don't panic. Okay. If I were you, I would just always write the absolute values, but since x squared plus 1 is always positive, they aren't necessary, okay? But I would just write them to be safe. Brainstorm with your pod what you think we should let u equal. Which means you have to talk to each other. All right, pod 5, what do you think?
You would have use tangent. Tangent of x.
So you think u should be tangent of x.
So then du would be secant squared.
So then du would be secant squared x dx. Does that work? Do we have secant squared x dx somewhere? We sure do. Here is secant squared x dx right there. So we can replace secant squared x dx with du, and what we have is 1 over u. Okay. Like I said on Friday, the more problems you do with substitution, the better you're going to be at seeing patterns. Okay, the pattern that you needed to recognize is, hey, if I let u be tangent, then we have its derivative secant squared in the numerator. Okay. All right, so the antiderivative of 1 over u is the natural log of the absolute value. And so our final answer is the natural log of the absolute value of tangent of x plus c. Okay, I have another one for you to brainstorm. I want you to talk to your pod about this problem. We obviously can't take the antiderivative right now.
Because ln of x derivative is 1 over x, and then we have, oh, we know we use next. Oh, x is 1 over x. No, because you would have this. Oh, you're right. Wait.
All right, let's all come together. Pod 2, did you have an idea?
We said that u would be natural log of x, and then du would be 1 over x.
Okay, anyone else come up with that? No, they weren't the only people. Okay, does it work? If u is natural log of x, du is 1 over x dx, do we have 1 over x dx? Yeah, we have it right here. 1 over x dx. That can be replaced with u, and then we have 1 over u. So just like before, we get the natural log of the absolute value of u plus c. And so our answer is awkwardly the natural log of the absolute value of the natural log of x plus c. It looks like an awkward answer, but it's correct. Okay. Now, I know there are a couple groups that said, oh, I tried something and it didn't work. Okay, well, try something else. If you try something and it doesn't work, obviously wasn't the right way, try something else. Okay, with these substitution problems, okay, there's not a whole lot of choice for what you can be, so if something doesn't work, try something else. Okay? All right. Throw you for a loop here. We don't have an antiderivative for tangent. Okay? We have an antiderivative for secant tangent, but we don't have an antiderivative for tangent. Okay? Now, I didn't talk about this on Friday, I waited till today. Why would I wait till today to talk about tangent for an antiderivative? Exactly. We can write tangent as sine of x over cosine of x. Right? And now we have a candidate for u substitution. If we write sine of x over cosine of x, what could we let u equal? Okay, I'm going to go with your sine first. If u is the sine of x, then du is cosine of x dx. Technically, do we have cosine of x times dx in our integral? Okay, we have 1 over cosine times dx. You see the difference? Okay, so this isn't going to work because we need cosine of x times dx. So instead, let's try u being cosine of x. So then du would be, thank you, negative sine of x dx. And we do have sine of x dx in our integral. Okay? So what we can write, because we have this negative here, so we can rewrite negative du is the same as sine of x dx. So when we rewrite our integral in terms of u, we have to make it negative. Negative 1 over u du. Okay, so we have negative natural log of the absolute value of u, which means the antiderivative for tangent is negative natural log of the absolute value of cosine x plus c. Following that same process, I would like you and your pod to come up with the antiderivative for cotangent.
It's increasing rapidly. It's increasing negatively. On my paper, I'm like, what? Oh, you just still hear the point. Yeah, I think you actually took off.
Okay, I hear a lot of talking, so I'm thinking that maybe we're getting through this. Grant, what's our antiderivative?
It's the natural log of sine of x, absolute value plus
Okay, makes sense that they would have similar antiderivatives, right? Okay, you don't necessarily have to memorize these because we can find these with U substitution, just as easy, okay? If you want to, you can, but I would just use U substitution to get those if ever I ask you for either one of those. Okay? 2 more examples, and then I'm going to give you a task. Go ahead and write this one down. What is different about this one compared to like the first one that we did? Connor?
There's multiple powers of x.
Okay, that is one. There's multiple powers of x. What's another difference? Irrational is not the word I'm looking for, but you're on the right track.
It can be undefined.
Where was the higher power in our first example? In the denominator. And it conveniently was 1 less in the numerator to where when we did U substitution it matched the numerator's power, right? Here we have a higher power in the numerator. What's true about a fraction if the numerator is bigger?
something zero.
Let's just think about like not even like algebra, like numbers. 5/4. What do we call 5/4? As opposed to 1 1/4. It is an improper fraction. And what can we do with improper fractions? I gave you 100 over 4, you would say. You would say 25. How did you get that? What's another word for we divided? Okay, if we have an improper fraction and we have no true, okay, we can't take the antiderivative right now. We can see that U substitution is not going to work. Here we have 2x squared plus 7x minus 3. If we let that equal U, like nothing matches up with that. Okay, but what we can do is actually divide an improper fraction. So let's flash back to what? Algebra 2? We're going to actually do some long division here. Okay, this is good practice for you here, people. Okay, x times what is 2x squared? 2x. So put a 2x right here, and we take x minus 2 times 2x. And what do we do with those two quantities?
Subtract them.
We subtract them. So we have 11x, and then we bring down our minus 3. X times what is 11x? What?
11.
Thank you. X minus 2 times 11 is 11x minus 22. What do we do with these two quantities? We subtract, so we are left with a remainder of 19. Let me remind you how we write this. When we take the division, we are going to have our quotient, 2x plus 11, and then we take our remainder over the divisor. So now this is the integral that we are working with. Jennifer, what is the antiderivative of 2x? X squared plus the antiderivative of 11. Larry? Antiderivative of 11.
11x.
Thank you. Okay. And then this we can think of as 19 times 1 over x minus 2. And since this is linear, you can use substitution, but you don't have to. We know that this is going to be 19 natural log of x minus 2 plus. If the antiderivative of 1 over x is natural log x, then the antiderivative of 1 over x minus 2 is the natural log of x minus 2. Okay? As long as it's linear, you can do that. All right, last example. I won't make you divide in this one. You're going to have some homework problems that involve e to the x. Okay. What is the derivative of e to the x? E to the x. What is the antiderivative of e to the x? E to the x. So if you are going to do u substitution involving an e to the x, okay, if you're going to let u equal something with e to the x, there better be another e to the x there. Otherwise, you may have a situation where you're letting your power of e be a u, and there should be something multiplied with e to help you out. Okay? So we do have the option of multiplying this out and then multiplying it to e to the x. But is that our only option?
No.
No. Since we have a composition times a function, we can try u substitution. What could we try to let u equal? E to the x plus 1 is inside a quadratic, which makes du e to the x dx. This is nice, isn't it? We have exactly e to the x dx. So our integral becomes u squared du. Aaron, what's the antiderivative of u squared?
1/3 e to the third. And then, oh, plus c.
Okay, good, thank you. And then we can change it back to x's. Okay, so 1/3 e to the x plus 1 cubed plus c would be our final answer. Now, just because you have a fraction does not mean it has to be a natural log antiderivative. you saw some fractions in your homework last night, right? Like number 19 was a fraction, but the denominator had a square power. Okay, that's still a possibility. Don't think because it's a fraction it has to be a natural log. Okay, like I said, the more problems we do, the more problems we get exposed to, the more comfortable we are going to feel about this. Okay, so I'm going to give